Hey all, welcome to ShareTrack. This is Raj here. I think we haven't spoken about CAR-T for a while, whereas CAR-T cell has actually been very successful in the clinic, and it has been getting a lot of approvals and curing a lot of people. I think around 20,000 odd people have been cured so far of various types of blood cancers. So I thought let's have a quick look at where CAR T cell therapy is at this point of time, and also just take a quick look at our genomic portfolio to see how many of our CAR T therapies are in clinical trial 1 or 2 or close to being approved. So that's what I'm planning to do today. However, before I proceed, I request that you take a moment to press the subscribe and notify button. I'm asking this because as per YouTube, only 36% of our audience is subscribed. This has gone up by 1% since my last request. So I'm requesting you once again, please do subscribe. It helps the channel and it improves the stature of the channel. And we can get really good guests and create a much better program. Subscription is absolutely free. So please do not hesitate. Just subscribe and press the notify button. And with that said, let's get started. Welcome back, friends. The concept of engineered CAR-T was floating around in the 1990s, and at that time, many could not wrap their head around the possibility that CAR-T could become a reality and would work as expected. All that changed in a matter of a decade as the FDA approved the first CAR-T therapy to treat leukemia in 2017, and that was just the start. I remember growing up, I lost a cousin of mine. He was younger than me, and he was a very nice little boy, but I was, I think, 10 years old at that time. He ended up having cancer, and we were all very sad when we heard the news. And I saw him deteriorate before my eyes. And in those days, cancer was a game ender, and many people didn't know how to treat it, and it was very, very difficult. Considering those days, things have changed a lot today. Right now, blood cancers are much more easily treated as compared to solid tumors. Solid tumors still need a lot of work to be treated. In our channel, we had a mini series that talks about human immune system, and in that I also specifically talk about the role of T cells, naive T cells, all the way up to maturing and becoming helper T cells and memory T cells. You can have a look at that series if you're really interested in T cells. CAR-T is basically a short form for engineered T cells that develop new chimeric receptors. And I'm going to explain that to you a little more in detail as we proceed further in this video. But I would seriously recommend that you have a look at the mini-series on human immune system. It had been developed with a view of enabling people understand genomics as well as various genomic cures that are being worked on by scientists for various genetic diseases and ailments. Before the advent of CRISPR, gene editing was a bit tedious and was done by two technologies. One was called ZFNs, or zinc finger nucleases, and the other was called TALENs, or transcription activator-like effector nucleases. Zinc fingers are segments of protein that have evolved to recognize and bind to specific DNA sequences. Knowledge gained from natural zinc fingers led to the development of zinc fingers nucleases as designer DNA cutting enzymes. But still, it was a lot more tedious. Then from 2012 onwards, CRISPR-Cas9 entered the scene, and many Cas proteins have been identified and processes have become more efficient and accurate. Alongside, we have had genomic sequencing hardware that became increasingly powerful and more economical, and genomic analysis software that have helped us expedite revolutionary approaches to cure disease and genetic disorders, pattern matching, and identifying tandem repeats and various kind of sequences helped scientists identify markers for various diseases. From the days of cancer being a death sentence, we are now in a situation where personalized engineered CAR-T cell therapies are created to cure a variety of cancers. It is estimated that currently there are around 500 clinical trials underway when it comes to CAR-T therapies. This means at least three things. There is going to be a competition among CAR-T therapies for ailments. the cost of the treatment is likely to come down. And finally, apart from cancer, other ailments may also be addressed by CAR-T potentially. All this is possible because CRISPR has made it easy to modify T cells and create CAR-T products. While great success has been had in hematology with CAR-T, it has been seen as being not as good when it comes to solid tumors. The overall strategy of designing a CAR-T cell revolves around properly identifying a unique protein or marker that can only be found on the cancer cell, or, to be a bit generous, finding a marker that is predominantly found in the cancer cell. This ensures that the engineered CAR-T cell can find and bind to these markers and unleash cytokines to kill the cells. And because these markers are found predominantly in cancer cells, most of the cells that get killed will be cancer cells. There would be a little bit of collateral damage, but it will not be too bad. The more specific the marker is to the cancer, the more accurate and surgical and elegant the cure. When the marker can be found in other cells as well, the other cells become collateral damage. So there is always this research which goes on to discover unique markers which are very, very specific to the cancer cell and yet readily available to the CAR-T cell. So discovery of unique marker for a cancer, it's the first goal. The next goal is to find a marker that is commonly present among multiple tumors so that a single CAR-T therapy can cure multiple tumors. Even if a marker is identified, the problem has been that many tumors release immune suppressing chemical signals and use up nutrients in their immediate vicinity to fuel their rapid growth. As a result, when the CAR-T cell approaches such tumors, the immune suppression enzymes secreted by the tumor nullifies the CAR-T cell, and also the CAR-T cell doesn't have adequate nutrition in the local area to fight the tumor. So work is now ongoing in trying to remove receptors that respond to immunosuppressive agents. And once the CAR-T cell is engineered to remove those immunosuppressive receptors, then the CAR-T cell can be much more effective in the vicinity of solid tumors. And there needs to be another way to identify some kind of engineering on the CAR-T cell so that they can prolong the nutrients that they already have, or learn to use the nutrients available while competing with the tumor cell in the location of the tumor. As per an article in Nature magazine, synthetic biologists have also set their sights on T cells and are engineering sophisticated cellular circuits that could allow greater control over the expression of chimeric antigen receptors and other proteins that might increase T cell activity. In December last year, synthetic biologist Wendell Lim at the University of California, San Francisco, and his colleagues reported that they had engineered T cells to express both a chimeric antigen receptor and IL-2, an immune-regulating protein. IL-2 can improve T cell penetration into solid tumors and overcome the immunosuppressive signals that tumors release. But it can also be toxic when administered systemically. Letting the T cells produce IL-2 enables local administration of the protein, which could bypass its toxicity to other tissues. Earlier, it took a long time to make CAR-T and identify targets. Today, thanks to advances in technology, the problem is that there is a whole lot of targets and CAR-Ts available and ready to go, but the in-human testing funnel is very narrow. When it comes to CAR-T, there are two types of therapies, as we have mentioned in our earlier videos as well, allogenic and autologous. Autologous therapies are easier on the body but cost more due to the logistics of collecting the cells from the patient and modifying them and putting it back into the patient. But on the other hand, autologous therapy has got less challenges of being rejected by the patient. Allogenic therapies, on the other hand, can be provided off the shelf, and they come from healthy donor T cells, and therefore they are very, very potent. But they need extra programming in order to ensure that they avoid the graft versus host disease and manage to survive in the body long enough to do the work they were designed to do while evading the body's T cells. If you recollect, I had covered earlier the commercial production of viral vectors needed to deliver these gene editing payloads into the cells, and how it is difficult to create the lentivirus and adeno-associated virus, AAVs, in sufficient concentration and quality. There is still work needed in this area to deliver quality viral vectors on demand. Right now, there's a waiting list for these vectors. Other delivery mechanisms like liquid nanoparticles or LNPs are also developing, and they may provide a bit of relief and a much more efficient method of delivering payloads. It is an interesting field to be in at this point of time, and one thing I forgot to mention so far is the conditioning regimen. The conditioning regimen still remains chemical, and it's hard on the human body. If a suitable genomic alternative is found for conditioning the body in a more gentler way, it would be really helpful. Magenta was working on MGTA 117, and the latest news which I delivered to you 2 or 3 days ago is that it has been put on hold due to the death of a participant in one of their trials. And I was looking forward to Magenta 117 being something that could really turbocharge all the genomic medicines that are being developed, because if the conditioning regimen is gentle, then the patient has got more strength to withstand the therapy, and also the patient experience is also much better through the therapy. Whereas we all know that chemical immunosuppression is very, very intrusive on the body, and it's very hard on the body with hair loss and vomiting and nausea and all those side effects. So that's one thing that I had forgotten to mention you. Once all these factors are taken care of, I think CAR T cells would make even bigger progress. But among all the gene-edited therapies that we are looking at in our watch list, CAR T has been most monetized, and the next best so far has been Zynteglo and Skysona. They are not CAR T cell therapies, but they are gene therapies, and they have been monetized. And I'm looking forward to more monetization this year for at least CRISPR Therapeutics for their sickle cell disease and TDT therapies. Now, to summarize, among all the cancer therapies, CAR T is making the greatest impact, and it is being felt in hematology. Solid tumors are a bit more difficult to treat at present, and CAR T cells need to have additional capability to avoid immunosuppression and nutrition depletion in the tumor site. Once that is done, then we can have more success with CAR T on solid tumors. Autologous therapies are very, very involved and expensive, while allogenic therapies are conceptually attractive but have a long way to go, because even if a reliable unique marker is found, allogenic CAR T cells have to evade the host's immune response and survive long enough to be in the body to be effective. There are many successful CAR T therapies already approved by FDA in the clinic, performing a great job. Over 500 more CAR T therapies are in the clinical trials right now, and many of them are likely to get approved this year and get monetized. Research is ongoing for prolonging the life of allogenic CAR T cells in the body, as well as discovering unique tumor markers to target the engineered T cell receptor. Many companies in our genomic watch list are active in this field, and some of them will end up with a successful therapy and monetize it. Probably not in 2023, but surely in 2024. Beam Therapeutics has got Beam 201 in enabling stage, targeting CD7. CRISPR Therapeutics has CTX110 and CTX130 in clinical trials, with CTX112 in enabling stage. Allogene has Allo501A and Allo647 in phase 2 clinical trials, with 501A scheduled to be targeting enrollment in first half of 2024. In fact, Allogene has a slew of allogenic CAR T therapies in its pipeline, with almost 40% of it either in phase 1 or phase 2 clinical trials. Caribou Biosciences has got CB010 and CB011 in phase 1 clinical trials. We had a little bit of a setbacks with CB010, but I'm pretty sure Caribou Biosciences will be able to proceed further. While the CAR T therapies currently available are expensive right now, it will get less expensive as the volume, technology, and competition grows. While I don't see much monetization prospects in our genomic watch list right now, I'm hopeful that CRISPR Therapeutics may monetize its sickle cell disease and TDT therapies this year. And also CRISPR Therapeutics may potentially have VCTX 210 achieving some milestones this year, which takes it closer to monetization. So this is all the thoughts that I had in my mind, friends. We have always been waiting anxiously for our genomic watch list to deliver some good news or the other. So I thought I'll let you know about CAR T cell therapies. So there is a hope in horizon for many of our companies, and CAR T cell will ultimately be giving a lot of revenue to the companies in our watch list in the years to come. That's all for today, my friends. Bye for now. I'll catch up with you again tomorrow.